I'll mute. I'm
Two
gonna mute.
two rich blades and a spring back are riding a prime power coach. To the wind drag a concave road, the universal infection of substandard cash put so much pressure on the scalar field that God gave in to the fabric of space and time. How many races thus are lost and perverse as a young man's brains is time's first pitch and toss when cosmic inflation bucks and goes in reverse. Interesting metaphors happening here. This is a poem by an Instagram poet named Elizabeth Elliot Poetry, apparently published by Winter Press in 2020. You can find this poem and other ones at elizabethelliotpoetry.com. But
Yeah, it's cool.
I'm not here
I need to
to.
listen to that. Yeah, I need to listen to that a couple more times. So.
I'm not quite here to just promote poetry. Let me
Oh,
put my
oh
face
no.
on. And there's a
But what
point.
is this? What? Wait a minute. What are we watching?
Okay.
What
Okay.
is this?
Fine. All right. So, we're as a disembodied voice in the background has stated, this is SG2 on Space, the only weekly space show. Missed one last week due to Christmas times, but we are back now. And if you're watching this live, um, you should know that today this is episode 218, and we're going to be talking about cosmic inflation. Um, Before I continue, I would just say support the show on patreon.com/SGT on space. Thank you for Kyle Baker, Sam Welsh, and John Grace for your donations. And of course, I need to bring on somebody else here. Let me see if I can do that. This guy.
Shen.
Who is this person?
Shen. No,
Who is
this
he?
way. Who is he?
You almost got it right, I think.
Well, I can see myself, so it's like it gets the drill.
If I point to my left, the camera actually points to the right.
Yes.
That's
Yes.
how it works on my
If it were a mirror, it would be, people think
They
it's
would be the
reversed,
same.
but then like a lot of people say, well, how come my left and my right are reversed, but my head and my feet are not reversed? In a mirror. When I'm talking about like in a mirror.
It's optics.
Well, yeah, it's optics. That's what you would call it. But I mean, so what the mirror does is it actually inverts the x-axis, the x coordinate.
Right.
Like
it doesn't reverse the y coordinate.
It doesn't. Yeah, the y and the z coordinate, it reverses the x coordinate.
So, but this really isn't like a mirror because really it's the vantage point from the camera. So this is my right hand. I'm using my right hand.
That's right.
And I am pointing to the left, but from the perspective of the camera, it looks like I'm going to the right.
Yes.
That's all it is. Okay. I don't know why I have to explain that to people. But
so. Well, I think it's good to have a little bit of delightful banter before we,
Delightful banter is right. Hey, your headband today looks like a crossword puzzle.
It is a crossword puzzle. Yes.
Oh, are you really? Like, that's not a joke. It actually is.
It's a necktie that is a crossword puzzle. So I'm using it as it. I don't wear neckties the way normal people do in the 21st century.
Understandable. It may be in the future,
or even in the 20th century.
This becomes Leonard. You may not know it, but you're an early pioneer of the next generation of fashion trends.
That's right. I'm the maker of manners.
Exactly. So in that sense, you're really ahead of your times.
I hope so. I think so. Yes.
All right. So.
What do you want to talk about? What do you want to talk about tonight?
The actual topic of the night. Can we talk a little bit about, like, if I just throw around the word cosmological inflation, it just sounds like a big word that most people have no idea what it is. Like,
right.
So, what is it?
Well, cosmological inflation. So, it's a theory that proposes a certain period of extremely rapid expansion in the very, very early, just fractions of a second after the Big Bang. And it's like a brief but intense burst of expansion that explains some puzzling observations. Observations such as like uniform temperature of the cosmic microwave background, what they call apparent flatness of the universe. What do you mean flatness? It's flat. Well, we'll talk about that. and the absence of magnetic monopoles. So
So according to New Scientist here, it's a faster than light expansion of the universe. And
yes,
why
right.
is it? Why do we even think it exists? That it happened?
Well, okay. Why do we think it exists is because, well, the only the thing that we can observe about the early universe is the cosmic microwave background, which is it's like the great fireball that existed when the universe became transparent. All right. Before that, between the time of the Big Bang, there was a kind of a exotic um, plasma. I guess some people say quark gluon plasma. That once it cooled down to a certain point, it condensed into matter, and then it became transparent, so that we can see it. So that's what we see. And so there's and so there were various sensor and telescopic observations of it have been undertaken in the past 25, 30 years. That's the basic observation that we made. We also observed that the universe is flat. So there's like a meaning it's Euclidean in a certain sense. So Einstein's told us that gravity will curve space, but as far as we can tell on the largest scales of the universe, the universe is utterly flat, and I think we'll talk about that a little bit, and then also we observe subatomic particles in the standard model, and Maxwell's equations and the standard model does not have any source terms for a magnetic field, but various kinds of models of what they call grand unified theory models predict that there should be something called a magnetic monopole. So uniform temperature distribution. Yeah.
Okay. All right. Go on. Keep talking.
I was just going to summarize all that gobbledygook. Was that we observed that the cosmic microwave background is an almost uniform temperature to 1 part in 10 to the 5th about. It's incredible. It's an incredibly uniform temperature, so that points on the 25 light years apart, and yet they're at exactly the same temperature, and that's a really hard thing to understand. And then the apparent flatness, and then the absence of magnetic monopoles. So that's why that's where this theory came to be. So the theory was developed by really, I guess it's owned by like 3 physicists. One's Alan Guth, and Alan Guth. I think he's from.
Let me see. Alan Guth.
Andrei Lind, who's a Russian guy, and he's at Stanford. Alan Guth, yeah.
This guy, that's one of them.
Yeah, he's mainly the guy that. But we have to recognize it. So
1979, Cornell. Wow. And then the next year he gave his seminar. Junior particle physicist. All right, go on. Sorry, interrupting.
So no, it's all right. So anyway, right now it's kind of a cornerstone of modern cosmology, and it provides a framework that aligns with those key observational things that we've been talking about, and enhances our understanding. But there's problems. There are some problems with it. And so, but let me talk about let me talk about the pro part, the pro inflation features first. And so the thing is as I say, observations of the cosmic microwave background are really crucial, as is the Hubble expansion. The universe is expanding. So these are key pieces of evidence that support the theory. So first of all, there's with the CMB, the cosmic microwave background,
which, we have something called. I'm just going to interject here and say we're not going to dive into depth into cosmic microwave background here, but you guys, anybody watching this, can see our numerous episodes in the past where we discuss it. All right.
Yeah, I think I believe we've talked about it before.
Yeah, we
Maybe
have.
it was
We covered
it may
it
have been
on
a
a more extensive episode.
okay. Thanks for verifying that. I was thinking maybe it was in a previous lifetime.
Lifetime? I'm
Yeah,
kidding.
but
Go on.
okay, but yeah, we discussed it earlier. So the observations about the CMB are that it's sort of like the afterglow of the Big Bang, and what we see is a sphere of this fireball, and we're kind of inside of it, and it's greatly red shifted so that it's actually very cold today. So, or it appears very cold because it's receding from us, and so the thing is, its temperature is just so remarkably uniform. Every direction we look, we only see a variation of about one in 1 part in 100,000, and that suggests that the early observable universe must have been in thermal equilibrium at some point in the past. And I think I've tried to talk about some issues with that in some of our previous episodes. Some questions that I have about thermal equilibrium implies maximum entropy, and yet we're not at where entropy continues to increase. And that must have something to do with gravity, and that also seems to address the contradiction with the applicability or the relevance of string theory, which is supposed to unify gravity and the standard model, regular particle. But never mind that. I mean,
that's a topic for another time when we talked about your issues with string theory. So let's not go.
So the so anyway, the universe must have been in thermal equilibrium at some point in the past, meaning that regions now very, very far apart have had time to exchange energy and information, so that it's all mixed together. It's very strange. It's really not, and it's not perfect. I mean, we do see undulations, perturbations on the microwave background, which are important for theories about dark matter and other things like that. So, but so they're like, I guess we would say, causally disconnected regions. And according to the standard Big Bang model, without inflation, the age of the universe and the speed of light mean that there hasn't really been enough time for light, or in that sense, information to travel between the widely separated regions, right? So, okay, like for example, 2 points on opposite sides of the sky are so far apart that light couldn't have traveled from one side to the other in the time since the Big Bang. So they're causally disconnected.
Assuming if you just have the Big Bang and you don't have cosmic inflation.
Well, this is actually something that is actually observed, and so cosmic inflation is trying to reconcile that. There's a really big problem. So that's what they call the so that's one element of the horizon problem. So the horizon, and we keep talking about the horizon. In this sense, the horizon is the maximum distance that information or light could have traveled since the beginning of the universe, and that without this inflation that Guth and his colleagues have proposed, the horizon is too small to account for the uniformity in the CMB across the entire sky. And it means that regions of space that appear to be in thermal equilibrium actually couldn't have interacted with each other, given the constraints of the standard ideas we have about the Big Bang and so forth. So the resolution of this. So what inflation does for us is it gives us a period of rapid expansion, and all of it's like inside of the time that the CMB was created. So it posits a period of very rapid expansion that would make the entire
rapid
fractions of a second. So it goes from a point to the size of a basketball.
Which is like, to us, I mean, that doesn't sound like it's that large of expansion, but really was
think about it this way. It's like everything in the universe starts at a point and expands in I don't have the numbers at my fingertips, but it's something like 10 to the minus 32 seconds. So a very small period of time where the universe expands from a point to the size of a basketball or the size of a basketball, a grapefruit.
It's actually a incomprehensibly rapid expansion.
That's right. And so this is the idea. And so I'm already kind of okay. We don't observe this. This is all a theoretical it's all a theoretical thing.
This is a theoretical event that happened in the past. Is there any way we could observe that it actually happened, or is that impossible?
we are entering an age where gravity waves, the gravity is the waves from gravity are able to be observed. And I think many episodes ago we talked about LIGO and the gravity wave observatory. That's
many moons ago or suns ago. We talked about that indeed.
Right.
We talked about gravitational observatories, if you recall.
Gravitational observatories. So gravity waves will penetrate and will allow us to see things back behind the cosmic microwave background wall. We'll be able, because really as far back as we're able to observe is the CMB, and we can't see anything further than that. But gravity will get out. So gravity waves will get out, and we're on, like I said, we're right on the threshold of being able to observe things. So that's what's going to be happening. We are going to discover some things in the next 10 to 20 years.
So you're saying with gravitational wave observatories, we should be able to, quote unquote, see the inflation as well.
Right.
Cosmic inflation. Okay.
Actually, that's kind of cool too, because in all of human history, we always use just electromagnetic waves.
Right.
So the way we observe the universe, the way we observe everything is light, and light is an electromagnetic wave. But when we're using gravity, then we can see with gravity.
That is pretty remarkable. Cool. I mean, it's not really a visual sight, I guess. It's more like I mean, you know what I mean. We're able to understand things. The only other feature like that are neutrinos, which you need to stop me, because neutrinos are some of my favorite. Right. So
fermions.
Getting back on track here, one of the ways that you talked about that we have to that we believe inflation happened is due to the resolving the horizon problem.
Resolving the horizon problem,
and that would explain what makes the entire observable universe pretty uniform, and also how light could have traveled from, I guess, one part of the universe to another, right? That's what I'm saying.
Right. So everything, so it said that everything, the only causes of fluctuations in the cosmic microwave background would have been little either quantum mechanical fluctuations, or actually, believe it or not, what they call acoustic, meaning like sound waves that would be coming off of the Big Bang in that little volume. And so those are still present in the cosmic microwave background. So if you think of like a point, which doesn't make any sense, physics fails when everything is at a point, right? So we don't know how that happens.
Right.
Like
physics fails, breaks down singularities. Yes.
So it's empirical in that respect. I mean, there's some kind of negative gravity or something of that order that causes everything to expand very rapidly, and so that there's some acoustic fluctuations and quantum mechanical fluctuations that are impressed on the microwave background, and because that's what it looks like. It looks like it'll do that. So that's what inflation does for us. So it's a period of rapid expansion, and allows us to understand why things that are tens of billions of light years apart are almost identical.
Okay, so that was so we talked about the horizon problem, the flatness problem. Did you explain that?
Flatness,
you kind of partially did, but flatness is more than just when we say flatness, it's more than just one thing that's flat, right?
Yeah. So it doesn't mean flat like a piece of paper.
It does not. That's
really what it means is you like the standard kind of geometry that we learn about is Euclidean, right? So like two lines that are parallel don't ever intersect. Euclidean. It's that kind of stuff. Euclidean.
What's the other types of geometry? Okay, go on.
Not non-Euclidean. Okay, well, so in Einstein's equations, there's a term for curvature. So we know that gravity, the amount of gravity present, really the density, will contribute to spatial curvature. So in cosmology, the universe can have three different kinds of spatial curvature. Okay, so if you have so it's the idea is like, okay, so the universe is expanding, all right? So if it keeps expanding and then it slows down, stops, and then starts coming back together again, all right? Because the gravity would start to, cause it to collapse. And they have, I guess there was a term for that, which I forgot, something like the Great Crunch, cosmic crunch.
Right,
so,
right.
So in that sense, we would say that the curvature of the universe is positive, and that implies a closed universe. And we don't think we're observing that. Okay. Now the other side of it is you could have a negative curvature, and sometimes so positive curvature is like for the Euclidean. So is like the surface of a sphere, like has a positive curvature. And negative curvature, sometimes you'll see in books of plate.
Hopefully anybody can actually see this, right?
Yeah.
This is what you're saying.
Okay. Now I'm not. Now don't pin me down too much on this because I'm not like a real expert on it. But the saddle shaped thing, I think that's what we call negative curvature. That's a model of negative curvature, and that implies that the universe would continue to expand and it would just keep expanding forever, right? So positive curvature is like it goes up and then comes back down, and negative curvature means it goes on forever. And zero curvature is what we call flat. Okay, so that's a flat universe.
You explained this. The observed universe appears to be mostly what? Euclidean, right?
Yes, this is something that's become more and more firmly understood as in the past, 15, 20 years, that the universe will continue to expand, but will asymptotically approach a zero rate, but never really quite stop. So if you can imagine, like it keeps increasing, and then it will very gradually stop. That's not completely true because there's dark energy, but that's a separate phenomenon. So I don't want to talk about dark energy. This has to do with the flatness of the universe that is observed, right? So the universe appears to be spatially flat,
right?
And that means the geometry is very close to Euclidean.
And you're saying this wouldn't make much sense unless we have inflationary theory in there.
That's right. So the main things that have been observed are in the CMB, the temperature fluctuations that I was talking about, and little acoustic signatures that are in the acoustic deviations. Remember, these deviations are like 1 part in 10 to the 5th, but they're resolvable with the observations that have been made. And so these satellite sensing, telescope sensing missions, they reflect an angular scale of those patterns that are consistent with flat space. And I don't mean that you can't have curved space locally. I mean, obviously we're orbiting around the sun, so we're in a curved geometry, but the big picture.
You have like a locally curved space. It doesn't
It
doesn't mean that like
that's
on
right.
a larger scale it's still Euclidean.
Yes.
So you might have like a tiny little blotch here where you have something gravitationally large like the
Yeah.
sun cause a little
Yeah.
dip, but for the most part it's flat.
That's what we're talking about. And so,
Right.
and also, so there's been observations of the distributions of galaxies, and I guess we're going to be getting more information about that from the infrared telescope, the Webb, James Webb. James, is
Well,
it
James
James
Webb
Webb?
Space
Yeah,
Telescope,
yeah.
like what
We're-
is what would that tell
Well,
us?
distributions of galaxies in the early universe, because we're able to
Oh,
see
okay.
much further back than back in time than we have in the past. So anyway, the papers that are written on that and the theories about the pattern of galactic distribution, it's all consistent with this idea of the flat space from the Big Bang to the present day. So okay, so here's the deal. All right, dark matter, dark matter, dark energy. These are all density. They all seem to show that that they support the idea that the universe is Euclidean. And also, in the 1920s, there was a Russian physicist named Friedman, who it was really cool what he did. Everybody was all excited about Einstein's equations, and he combined
Sorry, what's his name? Friedman
Friedman
equation.
Well, you could Friedman equations, yeah. Okay,
Let me find this guy.
the
Alexander
Friedman
1922.
Alexander
He
Friedman.
looks
I forget.
interesting.
Sure, everybody did. Yeah, he looks like. Come on, it looks like people we work with.
Yeah,
You know,
yeah, you're right. He looks like
he's one of us. Okay.
he has a giant forehead.
Yes.
But go on. All right.
He's a nerd. He's a nerd. Yeah. So
right.
What he did was really cool. Was he kind of combined thermodynamics with Einstein's equations, and so
Wow.
yeah.
Go on.
So that describes the expansion of the universe, and so all of the solutions, the Friedman equations, are consistent. To match them to observations, they indicate a flat universe. So the thing is, so there's like
okay,
yeah.
go on. Sorry.
So there's a metric. Okay, so now here's the hard part. Okay.
I mean, do you really have to explain metrics? But go on.
No, I mean it's a thing to measure, like so the density of the universe.
Mm-hmm.
All right, so here's the issue. Okay, with all of this stuff having to do with a flat. If we take inflation, cosmic inflation, to be valid, then the density of the universe needs to be extremely close to a very precisely determined number. And I think it needs to be precise out to 17 digits.
That's a lot.
So, okay. All right. I mean, if you're not like blown away by that, then I'm not articulating it correctly.
Can you just say that again? What has to be accurate up to 17 digits?
The density of the matter in the universe, and matter meaning matter energy matrix, everything having to do with this the mass of the universe in that volleyball, okay, in the first tiny fractions of a second when the universe began, has to be so extremely precisely determined that we would not have a flat universe otherwise, because it grows, it increases.
Oh, I see what you mean.
Okay.
Like
so if it yeah, and that number has to be exact to, from what I understand, it's either 14 decimal places or 17 decimal places. I kind of don't remember.
What is
any small if it was too big, then we would have an open universe. No, if it was too big, then we would have a closed universe. and if it was too small, then we would have an open universe. But it's not. It's better than Goldilocks. It should be. So to me, that's a really big problem. Okay.
I mean, it sounds like you just have to have this perfect scenario, but then that doesn't make much sense, right? Like, why did it have to be that number?
Yeah. Right. Well, so I'm brave enough to go into this, brave enough to go down this walk, and that is people who believe that there's a creator, an intelligent creator, can use this as evidence. It's as dispositive evidence, right? So somebody had to one theory is that there's some supernatural intelligence that wanted to make a flat universe, and they had to pick a number that was very precisely tuned.
So
Okay.
you're saying this ultimate creator being that many people commonly call God decided to pick this number, and hence
Yeah,
up to the precision of 17 digits in order for the universe to be flat.
Yeah,
Because anything else
yeah,
like wouldn't be able to explain it.
yeah.
Like,
Now, Alan Guth and these other guys, they wouldn't be able to publish that in the so they're all so what they're saying is, and I think it's the Andrei Lind, the Russian guy. Excuse me. So what they're saying is, all right, so it's just that there's a multiverse. This is more to them. To them, it's a notion. It's evidence of a multiverse. In other words,
so inflationary theory causes creation of multiple universes. That according to that,
it implies because of the tuning of this particular number is so precise. Then that's just a statement that there's a multiverse, and that we live in the one universe that's flat, and then the flatness is consistent with a universe that is conducive to life, right? So that we have this what they call
the anthropic principle.
yeah, that's what I was trying. I was struggling to remember
the
that word.
I used to read up on the stuff all the time about how like we're not really unique. It's just that the only reason we're able to question our place in the universe is because if it was anything else, we wouldn't exist. So we wouldn't be able to even question it.
Yeah. So I think that's nonsense. Okay, because it's not obvious to me that the universe has to be flat, absolutely flat, for us to exist. I mean, it could be, it could be a closed universe. We used to be comfortable with the idea that the universe was closed, or it might be expanding forever. I mean, so I don't know the answer to this. I think that this is a very serious, to me, it's a very, very serious challenge to inflation.
You do not like the idea of multiple universes, and you also do not like the idea of some deity deciding one number for us.
I don't express any desire or like. It's just that it's a very significant problem. I mean, I'm open to anything. I'm open to all those things, but I'm saying this fine tuning of this parameter, I think, is wrong. I mean, I think it. I don't mean it's wrong. I think it's that it. What is it like? It's not. It's a challenge to the inflation hypothesis. I think we should be looking for a theory that flattens the universe. We should be looking for some kind of natural process that will even out all of the.
So inflationary theory right now has that issue, but at least it tries to address, like, hey, this has to happen in order for the universe to be flat.
Yes.
Right.
Yeah.
Okay.
So
let's go on to. Sorry, go on.
Oh no, I was going to say so. I don't know what the answer. I'm sure that the authors of the inflation theory have maybe addressed this in some way, but it's a significant problem in my mind. The idea that the universe is flat and it's dependent upon the selection of a very, very precisely tuned number. I mean, that to me that's a problem, and then appealing to multiple universes is just as metaphysically driven as the appeal to an intelligent designer, right? It's just a prejudice, right? So they I mean, if this were a laboratory and we were looking at some, what we would conclude is, oh, somebody snuck into the laboratory and set the dial to this number, right?
I mean,
but we
Sorry.
wouldn't say, we wouldn't say, oh, there must be a multitude of universes and the dial can get set at random to some number, and then because it's at this number, then we conclude that's what happened. So it's a prejudice.
Before we go into this more philosophical arguments, can you talk about the monopole problem and how that is related to inflationary theory?
So I don't really, so the monopole. So what a monopole is? So it's
what
magnetic
is
monopole.
Let's just start out with that.
Some of these theories, and we can't dwell on it too much because I'm not an authority of what they call grand unified theories from the 70s and 80s. They predicted that gut grand unified theory. Yeah. So
monopole. That's what this is.
Right.
Well,
so
they predict monopole. Go on.
They predict that there are these things called magnetic monopoles. Magnetic monopole is analogous to an electric charge, except that it's a magnetic charge. And so I guess most people know that if you have a magnet, it has two poles. That is a north pole and a south pole. And if you break the magnet in two, you're not holding a north pole. Okay.
Yeah.
You break the magnet in two.
Like this picture shows, you break it in two, you just form north and south and north and south. So you never have a monopole. Yeah.
So this is something that Maxwell in the 19th century observed when he came up with his equations. Right. And so the Maxwell equations, which describe how electromagnetic fields work, it's really the first field theory. The terms that have to do with magnetism in the Maxwell equations are what they call source free. The terms having to do with the electric field are exactly analogous to the magnetic field, but they have a source term, which is the charge, electric charge. So there's an electric charge, which constitutes a monopole, electric monopole, and it have a plus or a minus, but there is no magnetic monopole, magnetic and plus, plus and minus. It would be interesting to study that issue. Like, so suppose we did have magnetic monopoles. Well, electric monopoles, electric charge, proton is consistent of quarks, and the quarks contribute to their charge and so forth. So if there was a magnetic monopole, would it have analogous magnetic quarks? And then also the electron is a negative charge. It just opens up a whole new whole area of inquiry that I don't think has been addressed really. But anyway, the grand unified theories predict that a big bang that would proceed in the classical way that we used to think would produce energies large enough to produce these magnetic monopoles. We don't have particle colliders that are.
Yeah, go on.
I was going to say we don't have particle colliders that are powerful enough to get to the energies that are needed to produce the magnetic monopoles. They're thought to be very massive particles, but they should be abundant. Given, and so the resolution is that this inflation from a point to a basketball size entity or volume would dilute the density of any such particles to extremely low levels, or even not any at all. So that's why we don't observe them today. We do not observe magnetic monopoles, and so that's where we are on that.
So there's a lot of unknowns. It seems like the grand unifying theory.
To me, the inflation is just I almost said it's just a theory, okay? But I'm saying it's a theory, but there's only one thing that we observe. Well, two things that we observe. We observe the cosmic microwave background and the things that I've discussed, how uniform it is, and the large scale structure, large scale distribution of galaxies and galactic clusters like that, and also the Hubble expansion. Those are the only things we observe, and that you're talking about some physics that controls what happened to the universe within just the very tiniest fractions of the second that it was created. So that's cosmic inflation theory, and it's widely accepted, but it faces these challenges, right?
It's the
And that
best
is
theory that we have to explain a bunch of these questions that otherwise,
I
right?
don't know. I think it's better to me.
Let me not make a grand
to,
statement like that. Actually, I let you.
to me, I'm really not satisfied with it. For a lot of the reasons that other people have observed, is that fine tuning problem. With that critical mass density, that just makes me shake my head. You should be looking for a theory that will flatten the space instead of depend upon like the dial being set. Right? Some kind of, I don't know, some kind of drag or smoothing, something that will smooth out the universe. And then there's, of course, no direct evidence whatsoever, right? So while it explains a lot of the large scale features of the universe, and I think I saw an interview with Guth, where he was really excited because he came up with this theory when he was a postdoc in the late 70s, and then it fit some other factors, and so he was really excited about all that, which is that's all good stuff.
Like a lot of people, if you come up with some, not a lot of people, but physicists, when you come up with theories that seem to be able to explain things, you naturally get excited about it.
Yeah,
and
I'm all about that.
Possibly ignore some of its flaws because you're the originator.
Right. And so this idea.
Oh yeah, go on.
No, go ahead.
Well, I was wondering if you don't like inflationary theory. I mean, what's the alternative?
Well, I mean, one alternative is, I don't know. We need to keep thinking about this. I'm actually comfortable with that.
You're comfortable with not having an alternative, even though you don't like inflationary theory?
I don't think this theory is very good. Right? I think people need to be thinking more instead of studying. Okay, I really am comfortable not knowing something. Okay, where most people are not, or a lot of people are not. Like they're looking for some kind of explanation that they can put in a box in their brain and say, okay, I understand that, I'm comfortable with that. But I'm personally, and a lot of other people, like this, are like me, we don't know. Okay, so here we have this inflation theory, and the people who promote it, they get to give talks, they get to go all over the country or all over the world and discuss it, and they get on YouTube and whatever. But these problems are serious, I
found it.
And so I think it's better. I think it's better to say, I mean, it's fine to postulate this, but don't let it run away and be it, to go on its own, because like I said, fine tuning problem, lack of direct evidence, that multiverse implication. Okay, where that's fine tuned. Okay, so that means that we have an existence of multiverse. So and anytime you see somebody talk about the multiverse, they're off in metaphysical land.
Right? I like to talk about multiverses, but
and comic or comic books like Doctor Strange, which is awesome, by the way.
The greatest science fiction, to some extent, always involve multiverses.
So that might be true, but it's fiction.
Okay, but let's
so there are other scientists, like our friend
this is interesting.
Roger Penrose, and also I've forgotten our South African.
This is a different theory right here, the ekpyrotic phase.
Okay, so this is a different theory, and this is attributed to and I can't remember his
Turok.
Turok, yeah.
Yep.
Yeah. What's
Turok.
His first name? He's in Edinburgh. And
yeah,
also,
we did a whole episode on Turok.
Yeah, yeah. So I very much appreciate the way he works. He's trying to keep everything simple, right? And he's trying to have as few parameters as possible. So I think that he's personally, I'm a fan of Turok, and I'm a fan of Penrose. So anyway, those are the issues that highlight the ongoing debate. And
explain broad features seen the cosmic
and
background.
I don't think that we should. I don't think we should settle on theories that appeal to multiverses or that have tightly tuned numbers. I think that we should say we don't know, and we need to keep thinking about it. So,
by the way, I just want to, Leonard, given your physics and math background, how would you propose people to understand the actual equations? What do they need to learn?
What do they need to learn?
Yeah, like this stuff.
Well, I think you should take a class in general relativity, and you'll learn about Einstein's equations. You'll learn about the Friedman equation. You could take a class. You could take classes or study cosmology.
Like, if I say something like scale invariant tensor modes, what does that mean?
Well, I don't know. I don't.
Okay, but scale invariant seems to me like is not dependent on the scale.
So tensors are tensors are a mathematical abstraction with an index, and so generally in general relativity, you have tensor fields, which means that there's multiple elements, usually 4 elements, and you can use them to calculate an interval or it's a formalism having to do with the metric of the space and the curvature of the space. That's why I say if you want to learn about this, you need to take courses.
You need to learn about tensor fields, and that's basically something you learn in differential geometry.
No, I would say you need to take a class in general relativity because Einstein learned tensor fields from his professor Minkowski, right? And so so you just need to know enough. You don't need to take a class in mathematics about tensor theory, because you're going to learn a whole lot of things that physicists are not really very interested in. All right. So, but you need enough tensor physics, tensor math, in order to do the calculations and understand the Einstein equations. Right. So, and it's true that tensor relationships are invariant with respect to transformations. Right. So that's what we're talking about. But and there you see Einstein the little G there.
It's used to express the curvature. It occurs in Einstein field equation. Gravitation describes space-time curvature. So, okay, general relativity here.
You see that equation that one you're moving up. G equals R minus. Okay, so G times R. So this is an equation that results from the curvature. There's two kinds of things. There's curvature because of the space is curved, and then there's also curvature because the coordinates change. The coordinates rotate, and so the whole thing about this kind of geometry is trying to account for all of those things mathematically. So that's what's going on there, and all of these things. This energy tensor, and these are physical relationships. So I would say that a class where you can go all over this kind of stuff, but not a class in Riemann geometry. Okay,
Riemann geometry. You don't need to learn. Well, you do need to learn a little bit, but not a whole class on it.
Right. I think you just need to learn what Einstein learned.
pseudo
So,
Riemann manifolds, differential and you can go down a rabbit
yeah,
hole here, I suppose.
that's right. It can take you off on into a rabbit hole. That's what string theory is. String theory is a branch of mathematics, right? But it has so much.
Right.
So much. And also that's another thing. It's like so the inflation Guth and that group, they appealed to grand unified theory of the 70s and 80s. Right. So where is string theory? I mean,
It doesn't. It's not even
so
part of it, is it?
that's right. So it turns out that string theory can be adapted to produce magnetic monopoles also. But
Right. Okay.
string theory is so adaptable. It's so adaptable that
We
it
covered
can
string
predict
theory in
anything.
the past. We're not gonna go into it here, but I think what Leonard you're saying is that you've never been a proponent of string theory because you can basically adapt the mathematics to explain whatever.
And also, it doesn't predict anything.
Right.
It only fits things, like dark matter. Okay. Oh, there's dark matter. Oh, well, we can incorporate that in string theory. It does. If string theory were a good theory, it would we would
predict it.
produce.
Right.
Yeah, it would say,
You wouldn't
hey,
have
you
to
guys
tweak
need.
it to
Yeah,
do that.
you guys need to look for dark matter. Okay, but the observations of dark matter started to become really firm, like about the same time that string theory was being developed, and it didn't. So I have a problem with string theory, and I have a problem with
So
inflation.
for a whole discussion of problems with string theory, you can look at one of our past episodes where we talk about it. But for now, Leonard,
Right.
do you have any lasting words on inflationary theory or cosmic inflation?
Inflation theory is an interesting theory. It has some flaws. I don't think that it's to me it's not the to me we need to keep looking. In other words, we need
Keep
to have
looking.
we need to have graduate students who are sitting down and thinking, right? Instead of saying that inflation is the way to go.
Right.
So right.
Apparently, the three original architects, Alan Guth, Andre Linde of Stanford, and Paul Steinhardt of Princeton, in 2002, they shared the Dirac Prize for the development of inflationary theory.
Yeah, but not the Nobel Prize.
No, not the Nobel Prize.
So
And then 2012, Guth and Lind were awarded the Breakthrough Prize in Fundamental Physics.
that's all.
Anyways,
That's fine.
You can win all the.
I think it's good work, and I think they're really smart guys. Okay, but this is a problem. That fine tuning thing is a problem. Appealing to multiverse is a problem. Appealing to multiverse is a religious impulse.
It's always easy to try to appeal to the multiverse.
Right. So if you hear
Big Bang.
multiverse,
Inflation.
yeah.
Okay. Wow.
I mean,
that's
it's
like one of the
okay.
first
It's
things that
okay.
happened.
Yeah. So
10 to the
Anyway,
negative 32 second after the start of the Big Bang. That's almost no time.
Yeah. Right. So it's the time it takes to expand from a point, and we don't know what's going on at the point, right? To I think something like a basketball or a grapefruit.
Right.
Everything that is was contained inside of a basketball. It's almost incredible, including all of the strings. Presumably all of the strings were all crunched together, all close together. And where was gravity? Gravity wasn't doing anything. So gravity under those conditions, gravity was negative, like it was repulsive or something. Okay, so
I think I might write the science fiction story. Now I think about this, about how you know how that number you just said was very finely tuned.
Yeah, the density parameter.
Yeah. So I'm just thinking a super advanced like alien civilization way back in the past figured out how to make new universes, and they just tuned certain numbers to make new universes.
Right.
I don't
so
know.
that would be
I'm not sure if that's an original concept. Probably some other people have already thought of this weird idea.
I mean, there is a simulation hypothesis.
That's true. That's also like that too, right? So,
Did we ever do a show on simulation?
I think we did. It's an interesting topic, that's for sure.
Yeah.
I mean,
Well,
I've tried watching for like signs that I am in some kind of simulation. You know,
little glitches in the matrix.
I look up glitches in the matrix a lot, actually.
Mm-hmm.
I haven't noticed any in my own life, but I read up other people's
have.
stories and I get intrigued. But then I'm like, if I go down this hole too long, I lose touch with reality. But anyways.
Anyway, that's all I had to say, or all I can think of right now.
So hopefully, once we get the gravitational wave telescopes, we can observe actually all the way back here, right?
Yeah, that's right.
Because right now we're optical telescopes. Pretty much, you can't see past the cosmic microwave background.
That's right.
So,
can't see back behind that. So everything else, all of these numbers here and labels and stuff are stuff that's not observed. It's just inferred from the theoretic, from extrapolating backward from the microwave background, and also from the Hubble, the Hubble expansion. In other words, the universe is expand. First of all, when Einstein, said, "Oh well, I need to put a thing in my equations to keep the universe from collapsing," because he knew that there was a problem there. So he had, I guess they call it lambda. Sometimes you'll hear this term lambda, and so Einstein put lambda in there. And he did that to keep the universe static, because he had a metaphysical notion that the universe was static and constant throughout, and that was the prejudice of the 19th century. And only religious fanatics believed that the universe began at a point in time, right? And so actually there was a Belgian priest who was also a physicist named Lemaitre. And then the cosmic, and then Hubble expansion was observed, and so he went to Einstein and said, "Hey, look at these. I did these calculations with the gravity and stuff like that." And Einstein looked at it and said, "Yeah, your math is right, but your physics is horrible." And Einstein.
I recall that. Yeah, I know the story you're talking about.
Right. So it turns out that the scandal was that actually the universe did have a beginning, just the way the Bronze Age religious writers said in the beginning. It's like the world actually did begin, and that was something of took a lot of inertia to get past that prejudice that the universe was not. Yeah. Really?
I do find that really interesting that people had a historical sort of bias against the fact that our universe wasn't always as static as it seems.
I think that's
the
true.
That the universe is eternally the same or something, which is...
That's right.
I guess that was... I don't know. I suppose people had to believe in some kind of stable foundation. They couldn't conceive of something originating.
So I remember being, I was sort of a precocious child, when I was 10, 11 years old, and I was reading, about stuff like this. And I remember thinking, the universe must be constant and static, and so when, and then that was also about the time that the Big Bang theory started to become commonly believed and understood, and things that I would read in, I had these Time Life periodicals and National Geographic and Scientific American that I actually read when I was 11 and 12 years old. So I know that not the typical kind of thing that kids would read, but
that's not true. I enjoyed reading those too.
Okay, so anyway, I was different. Well, we are different. Yes, that's right. We're different. So I do seem to recall that prejudice, and that the idea that there was a Big Bang, that or an origin was something that struck me as being, the simulation hypothesis is also a Bronze Age religious myth.
When you say Bronze Age, like you
Yeah,
just saying that that's antiquated kind of thinking patterns? Is that what you mean?
No. I mean, literally, it's a story it's a myth that comes out of the Bronze Age.
Wait. But simulation theory, I thought was like we're all a computer simulation.
We're a simulation. So a super advanced being or civilization or something creates avatars in a simulation of some.
You're saying the religious books that's been existing for thousands of years, in a way, they are essentially the analogous to simulation theory because they're also just things.
I don't think it's analogous. I think it's exactly the same archetypal impulse. The super advanced being created a simulation. Okay, you just don't like the terminology because if I said he created the world,
right? But the world could be a simulation. So so if we replace world or universe with simulation, then it's basically the same thing.
Then it sounds sciencey. You're right. It sounds sciencey. And Neil deGrasse Tyson can, do videos about we're most likely in a simulation and everything. And the funny thing is, like the first time I heard about the simulation hypothesis where it started to become popular was, I don't know, maybe 10 or 12 years ago. It's the first thing I thought of. I said, there's a book called Genesis that was written about 1200 BC,
right.
And it said so, and not only that, there's glitches in the matrix, like the Red Sea parts, and like miracles occur. All kinds of glitches are going on all the time in Genesis.
Yeah, I mean, it kind of makes sense. If you're in a simulation, you can just modify physics whenever you want to. I mean,
right. And so, like the master simulator is watching the system and kind of enjoying the show, and maybe he interacts with the people because he likes them.
But what you're saying, like, I'm sure a lot of people who believe in religions will
love it.
Not. I mean, I'm not gonna be like, you're wrong, Leonard. But
really,
because I don't right. Like, I can't say that. I think any kind of faith, any kind of like religious faith or spiritual faith, is just like the name suggests. It's faith. Like you can't use any I can't use any scientific arguments to prove for it or against it.
Right. So, like the inflation theory appeals to multiverse in order to explain this serious, really profoundly serious problem that they have with the fine tuning. So, it's no problem. There's just a multiverse, and the anthropic principle takes care of that. Right. But as I pointed out, the anthropic principle doesn't really take care of it.
From that scale level, looking at that, where you have to incorporate multiverses in a very specific density number, that requires a level of faith as well.
Yes.
Really.
Right.
So it's almost, yeah. I mean, it's almost like a religion in a way if you don't start looking at alternatives.
Yeah. So who is the author who criticized Freud, scientific author, and I can't think of the. He advanced this notion of falsification, science falsification.
What is science falsification?
It's the idea that a scientific theory, in order to be truly scientific, has to be false. Popper, yeah.
Yeah, Popper.
Karl Popper. Maybe we should talk about Karl Popper next week.
You know what? Let's talk about Karl Popper next time.
Yeah.
So Karl Popper talks about how to separate science from non-science, right?
Right.
And in order for a theory to be considered scientific, you have to be able to test it and possibly prove it false. So like,
Right.
so science, according to Popper, should be an attempt to disprove a theory rather than continuously prove a theory. So in other
Right.
words, the
So
possibility criterion, like you have to be able to prove a theory false, and if you can never do
yeah,
that, then it's not a good theory.
the job of a scientist is to attempt to prove their theory wrong.
Yeah.
Okay.
Very
And if I
interesting
could,
idea.
okay, so I can really get into trouble now. That's not what climate science does. There is no climate science that tries to prove that climate change is wrong. There is no that you cannot get a degree. So that's why I say that climate science is unfortunately not science anymore. So, but anyway,
I think
that's my.
this Popper's idea in philosophy of science is definitely very interesting.
It
And
is right.
I think it'd be wise for scientists to actually. I took a philosophy of science class once, and I really enjoyed it. And Popper was definitely in there. I think it's wise for like people who study science to know a little bit about at least something about the philosophy of it, right? To in other words, to
I
understand
think so.
when are they doing science and when they're not doing science.
Mm-hmm. Yeah.
Like it's not.
Okay.
It may not be so clear cut.
Right. We've been going on. Okay, we've been going on
this is
for over
going
an
on
hour.
for quite some time. All right, next episode we can talk about possibility and Karl Popper and what defines what actual good theories and good science is.
Yes, I
and
think
for
I would
anybody
enjoy
who has
that.
not read his book, Karl Popper's classic book, The Logic of Scientific Discovery. Have you read it?
I've read another one. Maybe that was the book. It's quite a big book, but I have read that. I'm not sure where it is. I think it's around. I haven't seen it in a while.
This book,
but
originally printed in probably German, I would think. Yeah, that's a German version. It's probably still in print. So, yeah. Science should adopt a methodology based on possibility because no number of experiments can ever prove a theory. Right. That would require like proving it's infinite times possible, right? But you only need one reproducible experimental observation can refute one.
That's right.
So, yep. Yeah, so maybe once we get those gravitational telescopes up, we could refute inflationary theory by something.
I think that the Guth, and by the way, I don't want to say anything bad about Guth and that group. I think that they're brilliant scientists, so and it's very worthwhile what they're doing. It's just that this issue about that fine-tuned thing is, to me, it's a very big problem. And like I'm also open to where I've gone wrong, my understanding about it. So,
there's so much to understand.
So I'm comfortable with, right. I'm comfortable. Right. Yep. I guess
we hit over an hour mark. I'm not sure how many of our listeners are still watching, but for anybody who wants to post a comment, feel free to do so even after the show.
Oh yeah,
for sure. Always.
So what do they go? Questions. Like, subscribe. I think there's a bell you can ring or something.
Like, subscribe, share, do all that wonderful stuff.
Yep.
So let me just say, hey, what is it? Hopefully, SG2 on Space, you can like, subscribe, share, watch some past episodes. In this episode, we talked about past episodes that you could watch to learn more about, for instance, string theory. There's other episodes that we talked about the cosmic microwave background. There's another episode we talked about simulation theory. We've talked a lot about rather interesting things in the past as well. So with that, thank you for all of our Patreon supporters as well, Kyle Baker, Sam Welsh, John Graves. You can also go to patreon.com/SG2 on Space if you wish to support it to keep the show going and make it better and better. And with all that said, we will see you next time. In the next episode, we will talk about the philosophy of science and Karl Popper's possibility theory.
Cool. Okay.
All right.
Good night.
Good night.
Namaste.
Namaste.
Hello. Oh, yeah.